What is interpretability at all? It is not at all what the output might be. It is about how you are actually getting that particular output is the most important thing. I am Ayush Nangia and I am very much interested in continuous learning for intrinsic interpretability or through intrinsic interpretability, and I will today touch on the topic for intrinsic interpretability. Firstly, let us talk about what is actually XAI, or like what is actually this whole field about. So this whole field is about interpretability, explainability and so many different terms. The first term that I guess everybody needs to understand is what is interpretability at all, right? So firstly, it is understanding how a model works. It is not at all related to what the output might be. It is about how you are actually getting that particular output is the most important thing, right? So you can explain each and every action of your model instead of just predicting, okay, why did it give, maybe in a dog or cat classifier it gives a dog, why that? Whereas explainability is deeper into the decision that it made. So explainability is required as a base point of anything that you will need for an output based, but interpretability is how the actual model is training, learning, inferencing and everything. So explainability is mostly inference based and interpretability is mostly everything, every aspect of it should be touched. So these are some examples of how these models have become explainable. You can probably use SHAP or LIME or some kind of particular technique that is explainable, but they are not particularly interpretable each and every step. So you cannot say when did it realize how dogs look like, or when did it realize. Whereas in decision trees you can pretty sure realize that if sunny weather was there, then it may not be a good time to play badminton or something like that. So let us come to more terms called transparency and fairness. So these are two things that are much different from just explainability or interpretability. Transparency is basically how open your model is, how glass box your model is. So transparency is basically you being able to understand the biases for each of the weights and what it is leading to. So this is much more closely related to interpretability, but interpretability is itself a term for classical machine learning in terms of inference or training, where this is in terms of maybe you are showcasing this model to some non-tech person. You can say this is a transparent or a fair model which does not amplify biases. So these are another two different terms. So now what is a black box? Black box, I think most of the people know that black box is basically you don't know how the output is getting generated from the input. So this is somehow happening and this is leading to limited decision making because you don't know how actually AI models work. And that is a big deal because if you want to actually implement them into public sector domains, or maybe you want to have decision making that is trustable, maybe you have a particular domain like loan approval. So you cannot just have a black box model that decides how people's life will be governed without giving a good enough reasoning that okay, maybe your credit score is low. So this is another slide. Another touching on the topic of explainable AI. What is actually happening in explainable AI is that interpretability is decreasing as the models get bigger. So this is one trend that we observe. So that there is complexity in each of the things. So if it is complex, then the transparency is much less. Whereas if it is a simple model, it is probably transparent. So this I think everybody knows and observes. So adding interpretability to a model is like mostly everybody knows about. I think so, sparse and autoencoders. Everybody knows about saliency maps, feature attributes, deconvolutions, something or the other after you train a model. So this is not really a peak topic that everybody is looking at, because everybody wants, okay, maybe we made a top of the art model, but they are not making it accountable for what it did or whatever. Yeah. So these are some basic things that you do is basically you have an ML model, you apply some other algorithm and then you get the explanation out of it. So this is a very controversial side, but I found a lot of papers and attributes, is that post-hoc explainers do not really have a consensus on everything. So this is a language model based post-hoc explainer. I think you can see LIME says okay, taste is the most looked at attribute in this. So this is GPT based and this is according to like I think so how relevant is this to gorgeous, and like then similarly how relevant is this to mouthfeel and how relevant. So it finds like these words are much better than compared to taste. So everywhere you can see some of the listings are different. They might be similar, but if I expect my system to be fully explainable or fully interpretable, and I have devised 5 techniques, hopefully they lie on like a particular curve where you can say, 5 techniques are saying the same output. And this is super interesting because this is for a vision model. So vision model, maybe, not a vision model, this is for a table model. The vision model also have a similar thing, but like here you can see, some peaks are there for this, like maybe feature 5, and feature 5 is not really, that much of a influence than compared to feature 9 in Lime. So basically Lime is a technique in which, you doing a post-hoc interpretability in a certain way, you have certain attributes that you, like basically you mask a particular portion of the image and then you see what is actually happening, where Sharp is more of a game theory based approach and it is more like, RL based techniques in DPO or something like that. So they do not agree. So I don't want a model that does not agree on how I can explain everything, right? So another point why I am interested in intrinsic interpretability. So one thing is that, humans can be fooled very easily. I don't think like humans know how to train the, models for a particular intuition, because maybe you're training a dog or class classifier, which is what you observe in these intrinsic models. Maybe you make a classifier model and it is focusing on that particular class because it was taken from a particular camera, not because it was taken with a particular feature. So sometimes that happens. So maybe you make an essay with like best of the best state of the art, but you train the model wrong a bit, and your data set has some particular features that you are not visible to. So then it will probably not work for your interpretability task also, because like saliency maps are generally pretty good way to just have an highlighted region which is like good enough. But like then again they vary for each and everything. Simple neuron weights are best because you have one connection and then you can just go from one connection, how much weight does it put to everything. So there are a lot of fallacies. One small analogy that is there is that a model is basically like a student and we are like the teacher that is giving it a benchmark or a test to do. So either the model can reason like deep thing or something, or they can just cheat, right? So they know somehow to look at some tricks and they can probably give you an answer what you want actually. So there might not be a guarantee that you actually perform that good on a benchmark if you'd never ever realize how the model is actually reasoning the step or how intrinsic it is. So you can just fool your teacher, right? So now let us talk about the most interesting topic, and what this whole talk will be about is prototypes. So there are a lot of ways to do intrinsic interpretability. Let me just introduce like a basic way. And there are a lot of ways like concept-based networks or something like that. So prototypes are essentially a representation of how a particular subset of your data set looks. So maybe you have a cat, so a particular, or maybe you have a drill bit. So you can just have a drill bit which with another angle, with another angle, with another. So all of that represent one drill bit, right? Or one particular class. So that is how one prototype will respond. So this is one prototype, this is one prototype, this is one prototype, this is one prototype. So prototype is basically an example of your class, if I have to put it simply. So a prototype might be a cat. So a cat image for a particular class, maybe home cat, and you have another picture of a different home cat, but they are of the same class, they are prototypes of the same class. So now there is a thing called prototype-based networks. So you can probably train on these samples instead and try to figure out which sample belongs to which thing. So you have basically your image. So I think this is a better image. So you have certain examples, and then you have an embedding layer. Then you can compare your query example with those embedding layer, and you can see which is the most distantly computed, and then you can classify that later on. So basically you get an embedding layer to basically embed it into a smaller dimensional feature, and then you have some other layer that is learning how similar they are. We will talk about this later, but this is like mainly there's another layer that is helping you to compare this with this, this with this, this with this, and everything, and then you can have a certain dissimilarity score, and then you can have a neural network there. The P1, P2, as you can see, this is a color. So this is a prototype of this. So this will be representing some score or some matrix that was learned using this image. After you embed something, you will get some answer, right? So that answer will be learned and kept here. So and that kept here will be compared with this. And then that comparison is gone here. And that is, let's just say, a score between 0 to 1. So 0 to 1 you get a score, 0 to 1 you get a score, 0 to 1 you get a score, 0 to 1 you get a score. And then you have a neural network here. And then you classify it using a softmax function. So you have some certain examples in your test image only, in your training set, and you remember those examples, or remember a particular feature set of those examples, and then you are able to see how similar they are. So we will be dealing with part prototype, like prototypical parts instead. So prototypical parts are much better because these are prototypes, right? Maybe I can make 1,000 prototypes or have thousands of images of cats. Instead of remembering how every cat looks like, I can just say, okay, maybe a particular part of a prototype is very important. Like a cat's ears are very important to distinctively identify how a cat looks like, whereas a particular eye of a cat is much more important. In this case, you can see the eyes are being identified, and this is a test image. And then you can see, okay, maybe the whiskers was identified. So instead of saving the whole image or making a whole image a prototype, we will use a part of the image as a prototype. Yeah. So this is like some of the difference or comparison. So instead of knowing how the input is, you are remembering a specific part. So this is the most interesting part. This is what I will explain in a lot more detail. So basically there is something called as ProtoPNet. So why proto? Because it's prototypes, right? P means part. So, and net is like, CNN or something like that. So it is basically able to produce an explanation for the whole thing. So let me just go through it later on in the next slide. In this, you don't need an autoencoder. You will probably train a CNN to give a smaller representation, right? And you will probably get a smaller image localization also, that this is the part that is being realized at your prototypical part, and not just, the whole image. Instead of the whole image, you will probably identify, okay, maybe the beak was the important part. So you can do that mathematically. So this is the most interesting. So maybe some pretty pictures later. So this looks like that. So basically you have an image. Instead of just having a saliency map like this. This is your saliency map that you will get from a CNN. You can take out all the layers, take average. Or you can get a particular part attention map also, like take out one node layer. So instead of this, you can do this instead, and I will tell you how to train it. But like you can probably figure out, okay, this part of the image looks like this part of that particular image that I saw in my data set. This part of the image looks like that particular part of the image I learned from that data set. So this is like an image that you're inferencing on. This is the image that you learned on. So that is super interesting, that you don't need to rely on just maps. So this is the whole like architecture summarized. So you have an image input, like particularly image that will be 224 cross 224, and then you have a backbone. You can get any CNN backbone, and then you have a layer of 1 cross 1 ReLU and 1 cross 1 sigmoid. They have done this to compress the layer a bit down, like realize more into the dimensional space instead of that. So now you have like, this is the whole archetype of what happens in the whole architecture, is that you have a feature extractor, then you do this particular feature map. Feature map is generally 7 cross 7 cross dimension. 7 cross, so I think it is a small feature map, but it is working good for them. So they are generally transferring it to the dimensional layer more, instead of just processing 2 to 4. Then this is the most interesting, that you have a prototype layer, and that will have let's just say 10 prototypes per class. So there are 200 class, so there will be 2000 prototypes, and each prototype will be 1 cross 1 pixel only, and the dimension can be the same dimension as this. And we are just computing the L2 distances. I know you can say cosine similarity is better. That will come into the VIT one. So that is another paper. So this is a 2019 paper, so they did not realize, maybe cosine similarity was much better. So then you just compute your L2 distance. So you just minus that particular thing with that, and then you get a similarity score using this formula. That is a similarity score for the whole thing. So you just convert your distance into a similarity score. And then you get an activation map, because what happens is like, so you give an image, you have some feature mask 7 cross 7 cross D, and then you have 1 cross 1 cross D. It will go here, it will calculate your L2 distance. It will go here, it will calculate it will go here, it will calculate. It will do that again and again over your whole grid. Then you get an activation mark using the formula, using a similarity formula. Then you will identify the 95th percentile of this whole, and then you will get the localized mask. So in the training part, you do SGD, but you only touch the CNN and the prototype layers. The last fully connected layer, this part, will never be touched. So we know, okay, there is a learnable parameter, and then we learn this parameter. This parameter is learned automatically. I'm not doing anything. We just specify that 10 parameters will be run per class. Okay, and then we compute this particular score. So this is per pixel. This is 1 cross 1, and this is 7 cross 7. So you do per pixel something maps, and then you get this, and then you apply this particular map to this formula, and then you get a similarity score, right? So similarity score is calculated using this particular formula. Okay, so this is 1 over log of L2 distance. So how far are they? That is converted into some similarity. Then you can get this particular map. This will be maybe 3 cross, 7 cross 7. Maybe you change this side, then it will be different, but it's 7 cross 7 only. And then you apply a max pooling function over it. Max pooling, I think everybody knows, right? 3 cross 3, and then you can say, okay, 95% of this using visualization is the interesting area. That's why the bounding box is drawn there. So then you can just say, okay, what is the maximum similarity score is representing the whole 7x7 matrix, and that will be fed here, and then all can be connected to a fully connected network and a softmax function, and you get a probability. So we just make these fully connected weights 1 for this particular class if we know that this is the image that is being, and the rest of the weights will be 0.5, 0, minus 0.5, minus 0.5. So let me talk about the training stages. So this is the most important and fascinating and very tricky, or they applied some tricks to it. So basically they have SGD. Everybody knows SGD, I hope. If you have any other question, you can ask. But you basically have convolution layer and you have prototype layers. Those two will be using backpropagation trained. But for the weight initialization of the fully connected layer, because fully connected layer needs to have something, right? Otherwise, how will you do backpropagation? So you will apply just one there. If you know that, basically 0 to 9, I am saying 0 to 9, P0 to P9, I am saying they belong to a certain class. I know classes, right? So let me just say there is a bird A. So bird A will be represented using 0 to 9. These prototypes will not be specified by me, but I just make them 1, 1, 1, 1, 1, 1. So the weight that will be traveled through this loss will be higher. So this network will automatically learn to associate this particular prototype with that particular class. The minimum of minimum. So what is let's just say, similarity score is there. So instead of similarity score, we are measuring the L2 distance. So whatever is the closest cluster is my least clustering loss, and whatever is the farthest cluster is my separation loss. So this is a very nice example. So you train it after stochastic, you will get like this. So these are prototypes, and these will be separated through the separation loss, and these will come closer using clustering loss. So they are like, it is very nice example is that, like a neutron, like an atom. So you get this step, you get a SGD, you do a sneaky trick, basically one and the other are bad, and then you get a complex as a function for loss. But this is a very simple function because you know how to do cross entropy. These two are like how new electrons or something like that. You want the closer part to be closer and the other classes part to be far away. So yeah, this is the fun part. So how do we associate a particular image to a particular prototype? So you know that a prototype represents a particular part of a feature of an image. So we can just say that we have this particular highest semantic score, and we can say the least amount of distance to an image, whatever image that we have seen, is actually the image itself, or the prototype is it representing. So you get that how associating you can do for one image, and then after that you just train your final layer that you never trained, which is this layer. So you can just train this final layer because you've trained all of this. You can just train this final layer on a smaller subset of your image set. So that is your fine tuning part, right? And these are some of the nice images that you can look at. So let's just say that we have Blue Jay. So this is what it has identifies the prototypes of that Blue Jay. So this is how you get the inference call. So you get an image, okay, which prototype or which score area which will be higher. You get a similarity score for this and this particular image, and then you just multiply that with your fully connected network, and then you get a final score contribution for a particular class. And then you can, maybe softmax it over. This is the most interesting example that I found, is that, when you have to identify, is this, then you will probably look at the hood to find the logo for the Honda thing. And then you will look at, maybe the wheel chassis or something. So the model also behaves like a human would, see how a Honda logo is there or not. So now coming to shortcomings, is that spatial rigidity is not something that is maintained. If you have a camera angle from left hand side, everything is left hand sided, it will never learn how to view everything right hand sided. That is a bad thing. Then semantically mismatches can happen. Maybe it is learning how this particular thing is like this because there is a tree bark or something. So you might learn about the environment instead. So that is why you can have a pruning step. That is what they have included. So 25% of the prototypes that you will ever learn are useless. So 25% of your network will be useless. So you can just prune that up, and then you will get a better network, right? And then limited expressibility, okay, you are learning it on your own particular data set. It's not a generalized model. Then transformations, if you do like perturbation noise or something like that, it will change everything because it might be looking up at that. So that is one thing that I was talking about. And then, if something is occluded or something, maybe it will not work. So this is not deformable. You cannot do right to left to right. If your particular images are in a particular format, like this is JPEG, and you take a high quality PNG, it will not work on that because that's how the model was trained. So that is one thing that people observed, is that if you give the same image, but you give it in PNG, which is much higher quality or something like that, then the model will look at actually some other part of the image. So you can probably say that. And then you can add perturbation noises and probably, say, okay, these part are the learnable points. So what lies ahead is these two models are the new frontiers. Is you can probably train a VIT, which is giving you much better output, and you can probably train a non-interpretable model to become interpretable for use case. This is much more interesting because you can segment out particular prototypes instead of just taking a bigger picture of that. So that is my blog. Yeah, thank you very much. Yeah.